he's basically guilty of what you might call sham reasoning. He knows the result he wants to find, and he's making it look like his theory is fitting those results. So that was the geological critique. And this made Lowell be extremely critical of geologists. He has, being a geologist myself, I always have interest when other scientists are putting geologists down. But here is a letter that was written by one of Lowell's assistants, is saying that Lowell develops his energy to hunting a few facts in support of his speculation, instead of looking first at the facts and limiting himself to avoiding the conclusions, which is what good scientists do. This letter was written by A.E. Douglas, who unfortunately wrote the letter to someone that then gave it to Lowell, who immediately fired Douglas. And Douglas then, here's Douglas. For some reason, I can't get this thing to go away on my, yeah, the bar. And I don't know. Yeah, see what you can do to get that to, yeah.
Where is your cursor?
Yeah.
Do you see the cursor?
I don't see the cursor. Maybe if we'd go leave this, we can get out of it.
Just hit OK.
And how about moving that one? Okay. Okay, so now I'll just go back to play. Okay, well, that's better. Anyway, to make a long story short, although Douglas was fired, he was able to keep himself employed in Flagstaff. He became the sheriff. He moved to Tucson, Arizona, and in Tucson, Arizona, he got a faculty position. He got a rich widow to donate the money to build an astronomical observatory in Tucson that was the beginning of the astronomy program in Tucson. One of the reasons I moved to Arizona from the University of Texas in 1981 was because Arizona had this fantastic astronomy, planetary science program. I owe it to Percival Lowell firing A.E. Douglas from Flagstaff. And it was one of the many lucky things that happened in my life. Well, to make the story further into the 20th century, Mars science didn't really advance a lot. The observations were being made with telescopes, and these continued to have problems, but technology advanced. And it was possible to get spectral data that could identify elements in the Mars atmosphere. Also, the patterns on the surface were the dark and bright patterns definitely existed. The lines were always problematic. So the dark patterns for a long time were thought to possibly be vegetation. It was known that these white areas occurred at the poles. But the spectral data began to show that those polar areas could not be water ice. They, at least the surfaces of them, had to be carbon dioxide ice because the temperatures on Mars were extremely low. And the atmospheric pressure was also very low, only about 1/100th of the atmospheric pressure. And the gases in the atmosphere were very different than those of Earth. Earth has about close to 20% oxygen, has very little carbon dioxide, and it's dominated by nitrogen. You can see there 78% nitrogen for Earth, 21% oxygen. But Mars is 95% carbon dioxide, which is an inert gas. and not something that we could breathe. That's why Matt Damon had the spacesuit on. So this was the state of Mars when the first spacecraft went to Mars. It was called Mariner 4. And this spacecraft did a flyby. And the flyby is an indication of something that was pretty interesting in planetary exploration. Probably the flyby could not have gone to a less interesting part of Mars. It picked a place to fly by, and it was nothing but impact craters. It looked a lot like the surface of the moon. Now, this was in 1965, and the US program was geared toward putting people on the moon. And there were some scientists, not geologists, by the way, but some scientists that said, oh, well, if the surface of Mars just looks like the surface of the moon, why should we be spending all this money sending more spacecraft to Mars? There was a kind of theory into the late 1960s that the surface of Mars would look something like this, a somewhat reddish color, although Mars, the red planet, it is not red, okay? It's kind of an orangey color, not truly completely red. The reason Mars looks red from the Earth is we're looking at it through Earth's atmosphere. That gives it a reddish color. But Mars itself, now that we've sent spacecraft, doesn't have as red a color. But it has impact craters. The geologists recognized that these impact craters weren't like the moon craters. They actually had a little bit of degradation. But it was thought that maybe that degradation came about by wind. So this picture shows some wind dunes. It shows some chains of craters that might be mistaken to be channels. But that was basically what Mars was thought to be until right around 1971, 72. That was the time when I was in grad school. And I didn't really think much of planetary science. Surfaces covered by impact craters were not my interest. But in the early 70s, something totally different happened. Something that got me to Mars. Not like that. That was actually done for another talk, not by me, but someone else. By the way, this thing is going to be done more expertly by artificial intelligence now. So you're going to see more of this kind of stuff. It's not scientific, it's fake. And in science, we would never do that sort of thing. But what happened 50 years ago, this spacecraft orbited Mars. And Mars was trying to hide, just like it was in Mariner 4, because there was a global dust storm when the spacecraft arrived. It arrived with some Russian spacecraft. I think it might have been Mariner 8, but there was a mission where the US spacecraft and the Russian spacecraft arrived. The Russian spacecraft actually put the first landing on Mars, but it failed basically just after landing and sending a signal back. So Russia was, in competition with the US at this time. But their orbiting spacecraft just could look down at the dust storm, and that mission ended, but Mariner 9 was able to continue. The dust cloud cleared, and there was a total shock as to what was on the surface of Mars. There were channels, not the ones that Lowell thought about. These were channels that had been made by running water. So here was this planet that was thought to be dry, just a dry desert with impact craters that had been dissected by water. Not only were there these smaller channels that have networks like we have on the Earth, there were immense channels. And those immediately got my attention. There's the Mariner 9 spacecraft. This was the imaging system. It looks like one of those old television cameras from the 1950s because essentially that's what it was. It was a Vidicon imaging system, not digital. It just took these grainy looking, it looks like the old TV sets from the 50s. That's the kind of images, but they clearly showed, now here, the pattern of the drainage have been drawn in, but here you see some of the actual imagery from Mariner 9. It took about 9,000 images, and the important one for me, I'd just done my PhD dissertation studying the Channeled Scabland in Washington State. So I had studied perhaps the most remarkable megaflood landscape on Earth, and here were megaflood landscapes on Mars. The only difference was they were much bigger. So the megafloods that produced the features on Mars were immensely bigger. They were also immensely older. So here you see this pattern. We call this an anastomosing. The channels separate and they reconverge. But you see impact craters. Those impact craters are millions and hundreds of millions years old. So where we've been able to calibrate ages of the surfaces for these channels, many of these features are 3 billion years old or older. There are also streamlined uplands. So in the upper right, you had flow coming from the bottom of the image and going up toward the top. There's other remarkable things. Some of them clearly were sourced by impounded water on the surface, but others, this one is an example, although you don't see the whole thing, emerge from underground. And that water is coming out from the inside of the planet. Now, there were arguments about whether it was water, but the simple way that was resolved is that water is a large-scale fluid flow that is very fluid. It isn't like air that can't really erode very much. It isn't like lava or ice that is much more viscous and moves more slowly. It was highly turbulent. And among the possible fluids, basically what happened on Mars had to be done by large-scale water flows. So here are some examples on a map where this canyon system is just about the width of the United States from Oregon to Massachusetts. And the big channels are all at the top. The one we'll look closely at is K. It's about 4,000 kilometers long. And it's sourced at these depressions. So there are big depression areas all along here, and there are big channels that go toward the low-lying area in blue, which is the northern plains, from upland areas that are indicated by red. And the next images are going to show the downstream part of that K channel, which is called Kasai Vallis. So here is that, and you can see here's 100 kilometers, about 60 miles. So these features are really big, and several hundred kilometers with streamlined uplands, converging, diverging, very much like the patterns that we see in the Channeled Scabland. So when I saw these in the early 70s, having been I was not hired by the university to do planetary science, but I immediately became a planetary scientist. I changed the things I was doing just because of what nature presented to me. So here's some more detail on that same area, some of the names of the features. The yellow and orange are the high-lying areas, the blue, the low-lying areas. And you can see how it was clearly created by incredible, huge flows. Here's a little more, I don't know, almost psychedelic rendition of the same area, high areas in red, the lowest areas in light colored, these streamlined uplands, obviously created by incredible dense fluid flows, just like in the Channeled Scablands. And that became some of the early published work I did on this topic. So I have in this forum and other places talked a lot about the Channeled Scabland. Back in the 70s, we were beginning to get satellite images of the patterns in the Channeled Scabland. Here is one of the Landsat images. Spokane is up here, the Grand Coulee over here. You can see a sketch map of the same areas with some of the features, the ice lobes to the north, this greenish area being the areas that were inundated by the flooding. And you can see here in the Cheney-Palouse Scabland, you have flow that is converging and diverging around these speckled areas which were not flooded. These were streamlined by the flood flow, very much like the image that one had for this system called Kasai-Vallis on Mars. Kasai is a Babylonian name for the planet Mars. One of my PhD students who was actually mapping this area named his daughter Kasai. We geologists get really into what we work on. Anyway, so here's some detailed mapping of some of these features in the Cheney-Palouse tract. Here is a aerial photo of a streamlined island. It's actually the one over on the far left in the map area. There's some, you can sort of pick out some of the streamlining and the eroded land basalt. So all of these things were worked on in the 1970s when I was supported by research money from NASA as images were being produced by a later mission called Viking. Viking was the first big landers on Mars that were able to operate continuously. And these landers were intended to discover life. NASA had orbiters that the primary purpose was safety for the landers. This is an interesting aspect of NASA. It is in tremendous fear of losing spacecraft because then the money would go away for missions because they will have failed. So they had the orbiters able to produce really high resolution pictures to be sure that the place the landers would be put would be very safe. Well, those pictures were great for geology because they had the best resolution. In fact, even today, we have one of the camera systems that is used for Mars called HiRISE that can image an object the size of a soccer ball on the surface of Mars. Now, there are military satellites for that, but commercially, you can't even get that for Earth by paying money for it. The military has it, though, of course. But for Mars, you can see this stuff. You can go online and see it. So here are some of these streamlined islands. You can do a very sophisticated hydrodynamic physics to show how these things develop, or you can do what this guy did, who actually figured out, and you see the nice streamlined island and drew all of the flow lines around it. How many know who the scientist was that did that one? It's done by Leonardo da Vinci in the 15th century. He figured out this for islands in the Arno River. So this is, Leonardo was a genius. He wasn't just a painter. He did science and hydraulics. So that's how streamlined islands form. And they form on Mars and they form on Earth. So here's some more detailed mapping of the scablands that I did about 15 years ago. And it shows a little better this converging and diverging pattern that we see on Mars. There's some other features, though, where the water was ponded, like here in the Quincy Basin, by structural trends and uplands that are indicated by this dot pattern. The water flowed over divides, and where it did so, it eroded deeply, creating features like dry falls that some of you may be familiar with, and also big cataract systems. So the picture I'm going to show you next is from one of these cataracts called Potholes. It's located right there. It's actually in a divide that was cut across a low anticline. So here's the Potholes cataract system. You can see the roads on the floor. So, you know, this is big. The Quincy Basin is now irrigated agricultural land, fine-grained soils. That's why there's all those crops. But the eroded basalt, of course, can't be used for the crops, and it's now a state park and a wildlife area. But basically, if you had a rather normal river over this would be a waterfall. The reason we call it a cataract is that the water was, you know, many tens, in some cases hundreds of meters deep that were flowing over these things. Well, the same thing happened on Mars. Here is a cataract in Ares Vallis, and this one is 20 kilometers wide. And you see the pattern of linear grooves that is related to the streamlining of flow. This is about 400 meters high, this cataract. So this is similar morphologically to what we see on Earth. It's just a lot bigger, meaning the floods were a lot larger. So what we do in science is sometimes we have a theory and we make a suggestion on the basis of that theory that we call a hypothesis. We do an experiment to see if that hypothesis replicates what it predicts, and then we try to see if that tells us what really happened. In other words, we confirm or disconfirm the hypothesis. We can't do that in geology. And in fact, we can't do that in a lot of science. You can't do it you can't put the whole Earth in an experimental laboratory and manipulate it. We can't put a catastrophic flood in an experimental laboratory. So in geology, we have to do a different kind of thinking. And that thinking is called retroduction. Probably haven't heard that word, because the philosophers of science who describe science generally describe physics, not geology. In geology, we look for odd things on the landscape, like the Channeled Scabland. We try to figure out how that odd thing came about. So this is a very famous geologist. His name, Grove Karl Gilbert. And here he is in 1903 in Yosemite National Park, and he has found an odd thing. And this odd thing is a surprising fact. So the geologist begins with the facts, not a theory, with the facts. And we try to reason that if some causative circumstance was operative, this would come about as a matter of course. And so there's reason to suspect that this would lead to A, and that doesn't prove it's true. It just proves that this is something potentially to think about as we investigate further. So also from Gilbert, he points out that geologists are investigators rather than theorists, because basically the geologist is looking for facts that might overthrow the theory, and the theorist is more interested in the facts that sustain the theory. So the theorist, unfortunately, Lowell is a bad example of a theorist, but he was an example of a theorist. And that's why he could never understand geology. For geology, we use theory, but it helps us explain the facts that we've already found. And the other aspect of this is science is not really about a whole bunch of facts, what we call knowledge. It is an attitude that characterizes a community of like-minded investigators, a whole group of people that are dedicated to the search that nature presents to us. And that's all geologists think this way. And there are lots of surprises still left. One of the interesting things about these Mars channels, and this is still not resolved today, is, yeah, they emerge from underground, and this is one called Ravi Vallis. It's a couple of 100 kilometers long, maybe 10 kilometers wide. This is its source area. It's a clap zone with lots of big, blocks that have dropped down. So clearly, the fluid emerged from the subsurface, and the place collapsed over it. So the stuff was coming out underground. Some think it was ice. Some think it was water under the ice. May have been liberated in part by the effects of a volcanic sill underneath. It may have involved some kind of phase transition in a ice that was rich in a gas like carbon dioxide. But whatever reason, the water liberated comes across the surface, more collapsed zone. And then in this case, it disappears into a big depression. In some cases, it's really weird because in this one, Hebras Valles has a source area near the bottom, and then it ends abruptly in an area shown in B. And here's a detail of that area shown in B, and there's big holes, and the fluids just went underground, kind of like Mars is. There's immense caves down there into which all of this water is disappearing in the subsurface. We still don't fully understand how that comes about. Well, those are interesting geological paradoxes that are coming about from the observations from satellites. But there have been a whole lot of lander missions, as well as more advanced satellite missions. So I mentioned the Mars Pathfinder mission, 1996. I was involved with that. You can see on my back of my t-shirt, basically the team from the orbiter at the same time was called Global Surveyor. That was used to pick the landing site. The Pathfinder site, you can see there, was very near the Viking 1 landing site. We've had several later landers. We had Opportunity and Spirit, which were the Mars exploration rovers. We had Curiosity that I'll mention, which landed in a big crater that landed in the early 2000s. Current lander that's getting a lot of attention is the Pathfinder lander that landed in Jezero crater. Not shown here, just up to the right of the R in crater was a Chinese lander called Zhurong, landed 2021. Okay, I'll get to Zhurong because it hasn't gotten a lot of press. NASA doesn't put out what the Chinese are doing. Zhurong did some very interesting things, and I happen to have found out about some of them. Okay, so here's from Pathfinder. This is what the Pathfinder landing site looked at. And as a geologist, you see those hills, they're actually streamlined hills. So there was immense catastrophic flood flow that came across the surface. And these are big boulders. But the geologist would immediately recognize that the boulders have a kind of shape to them. They're all bent one way. This is called imbrication. These boulders were swept by catastrophic floodwater. And the landing site is basically in a catastrophic flood channel. Well, here's another place with big boulders swept by catastrophic floodwater. This is the Ephrata Fan in the northern part of the Quincy Basin in the Channeled Scabland. The Grand Coulee is up in the background. Here's another part of the surface of the Ephrata Fan. That's a big boulder that's about 20 meters in long axis. It's one of the biggest boulders that was moved by the catastrophic flooding. And here's that landscape with the Sojourner on it. By the way, the mission team tested the prototype of Sojourner in that Channeled Scabland area that I just had the pictures of, among those boulders. That's where the testing was done for that lander. Okay, so here are a lot of the recent missions, not the most recent. Zhurong isn't on here. The most recent American lander at Jezero Crater, that's not on here. But here's lots of satellite images and landing images. It doesn't have Zhurong on it. I've been involved in a number of these. This was an interesting one that was done out of my university. It was at the top, the Mars Odyssey used gamma ray spectrometry to map out the distribution of near surface water on Mars. And that map shows the concentration of near surface water where the blue areas have higher concentrations toward the pole, and then lower concentrations are in the more earthy colors. It turns out that we now know there's a lot of water near the surface of Mars. It's just in the form of ice. These are radars that are on satellites, basically the Mars Reconnaissance Orbiter satellite, that penetrates a certain area of sort of table-like mountains. And there are reflectors. You can see these bright zones here, the arrows under here. Those are bedrock under ice. And they are showing that there are basically dormant glaciers covered by debris that are on Mars. And we now know the amount of water that we have imaged directly, if you spread it over the surface of Mars, would be 20 meters deep. Okay, that's the water we image directly. There is probably, and there's a recent paper that just came out in the journal Nature, that very deep in Mars, down to a depth of maybe 17 kilometers, much more water. And Mars seems to have a huge amount of water deep underground. That may have something to do with this thing of the water coming out of the subsurface early in its history. So I'll mention briefly some of the current lander missions that are going on today. These are much more, they're rather big relatives of Sojourner. This is Curiosity. NASA puts out sort of contests for people to submit names. This landed in a big crater. It's many tens of kilometers across. It landed over near this channel. It is called Peace Vallis. And the low-lying areas are depression, so they had to pick, there's a lot of rugged topography. They had to pick a rather flat area to land. So they landed down in that area there. When they landed, some people thought that what I'll show you was a big surprise, but actually the geologists recognize certain kinds of features as distinctive for the processes that cause them. One of them is called an alluvial fan, which is where in the upper left, a flow comes out of a rugged canyon and comes out into a basin. These flows are generally produced by floods, not the really big ones, but big enough to move boulders and other things. And here's an example. You can tell from the road, it's not on Mars. This is in Death Valley. And you see the playa area of ponded water and the canyon and the distributary pattern of the various flows that have come out of the canyon. This is Mars on the left. You can tell impact craters all over the surface. Those are clearly alluvial fans. So the landing site for the Curiosity rover was in this depressed area, sort of to the lowland near the central peak in the crater. And from imagery that was produced prior to the landing, they could see that coarse sediments were in the area labeled by alluvial fan, and finer sediments were in the areas in red. So they picked that area to land. Now, when they landed more toward the coarse sediments. And people thought, well, it lands, and they immediately take a picture of what it landed on. It landed on flood gravel from an alluvial fan. The first pictures they took are the evidence of water flow that was being generated on Mars from alluvial fans. And the geologists knew this, but, and you can see the picture of that larger cobble. So these floods were significant, not a 20-meter one like we have in the Scablands, because this isn't really a really big channel, but Mars has fluvial activity that occurred all the time. So here's another comparison. That's Mars on the left. This is a conglomerate on the Earth on the right. The one that's been in the news from the US point of view is the Perseverance lander. This had a little helicopter, so it had a lot of press for being able to fly that around. It's a big monster. It's about the size of an SUV with this big arm that comes out, can do all kinds of high-powered analyses. It landed on the flat floor of this crater. It went up onto a what they were calling a delta, but it's increasingly looking like this was a kind of flood fan, because it's got a really big valley that comes out into it, and you have really coarse boulders that are covering the surface of this thing. So some of the recent results are suggesting that much more intense flooding was associated with this. Well, I don't have time to go into some of the fascinating features that we've discovered on Mars. One of the most controversial has to do with the fact that these big channels you see in a cartoon map there, and these are the ones I showed before, like Kasai Valles, they all go toward the northern plains of Mars, a lowland. One of my colleagues at Arizona, in a paper that we all did together, called it Ocean Borealis. And there are features that look like the margins of a water body is basically covering the whole northern part of Mars. Down on the lower left, the channels are shown in purple, the location of this water body. There's also evidence that there was basically a river system that started at the South Polar Cap, which we now know is mostly water ice. It's just covered with carbon dioxide for a lot of the year, a thin layer of carbon dioxide. That ice had melted in the past, filled an impact crater, spilled through multiple impact craters, and actually went to the northern plains. It would be like on Earth if we had a water flow that went from Antarctica to the Arctic Ocean. This actually operated on Mars in its ancient history. Here's an image of Kasai Valles taken from a different perspective with the highlands. Here's Kasai Valles. That's that area I showed you. There's the northern ocean basin. When I first described these, I had colleagues, not geologists, who said, oh, that can't be a river. There's no delta. There's no delta where that goes into what you are calling an ocean. Well, is there a delta at the mouth of the Columbia River? No. There is at the mouth of the Mississippi River. The Columbia River had massive floods. 16,000 years ago, we'd be under what, 120 meters of water at this location. So these Martian things, that one, outflow channels, they weren't rivers, they were catastrophic flood channels. But there's another part of the story. There was an argument over whether these shorelines could actually be evidence of the ocean. And water bodies actually don't necessarily have great shorelines all the time, because sometimes things go in the opposite direction. This is something I was able to study because I'm interested in big, massive flows. And in 2011, there were fantastic huge flows that were associated with a subduction zone earthquake, not dissimilar tectonically to what lies off of the Oregon coast. And there were tsunami waves that reached depths of 40 meters that came in off of this event. Here's one. I mean, these are houses, animals, unfortunately, people that are in this as it's coming across the landscape. And that happened on Mars big time, because you had impacts into that Northern Plains Ocean. And so here's the channel system, and here are basically features that were thought to be initially strand lines. These have turned out to be the terminal zones of massive tsunami that came out of the Northern Plains Ocean. This was a team of people did this. There was actually a team in the US that I was on, another team from from France. They both came to the same conclusion, very controversial, but interesting result. This didn't make much news because it was China that did it. Their lander landed in the Northern Plains. It actually landed here in this area of Utopia Planitia. Here's what Zhurong looks like. Almost looks like a little robot or something, but those are just its sensors. And Zhurong found sedimentary rocks. This wasn't reported in the news media in the US, but I was able to get, the Chinese published it in one of their journals, but they basically interpreted these as marine sediments. So you have tsunami deposits, marine sediments, shorelines, a whole lot of stuff that also has large channels that are feeding into it. Well, a number of years ago, my colleagues and I, as I mentioned, published the idea that we actually had an operating kind of Earth-like system with this water body. See on the left, the Ocean Borealis with evaporating water, precipitation, lakes, glaciers that were feeding a Mars that basically, if early Earth looked like this, early Mars may have looked like that with water bodies on its surface. Here's a depiction of that system that flows from near the South Polar area through multiple channels all the way up to the Northern Plains. This is all highly controversial today, but hey, what about the Channeled Scabland? I talked here 2 years ago about Brett's and his controversial ideas called outrageous geological hypotheses. That's what we do in geology. And it goes on. There's more stuff to discover. And so I'm happy to be able to share this with you, talk about my favorite topic, really big floods. And I've been lucky to have been part of the things I'm talking about here. So if you don't have any questions about this, well, that's too bad. Because you really should. And I'm happy to talk about those. Thank you very much for the opportunity.
Thank you so much, Dr. Baker. Do you have any questions? There's so much to think about here. And at the beginning, any of this is thought. No. Other than Dr. Baker. And it's fascinating. And that is gorgeous. Is that Mars right there?
Yeah, it's a European rendition. It basically they took the globe, they took various. You can go to Google Mars. You can get Mars data like that, but they had to fit it onto a globe, and of course they added some lettering and the like, and they colored in the what would have been the water bodies. So it's partially actual data, some interpretive material put on top. It's not like the picture of me walking on Mars. This is actually something we use for real science. The Perseverance rover, the one that's operating in Jezero crater, is caching samples. It is taking samples, basically cores, and putting them into a sample container and leaving them at specific locations. Now, the idea is some future mission, maybe with technology that can aid it, will then be able to go back to just get those samples, take it up to an orbiter of some kind, and then have a capability to return it to Earth. This is very difficult to do. It's hard enough to send something to Mars and then leave it there. Many spacecraft have been lost trying to just get to Mars because unlike Earth, which has this atmosphere that slows things down when we come into it, Mars doesn't have much atmosphere. So the spacecraft is coming in at high velocity. Well, that's what meteors do. They come in at high velocity and they just go splat on the surface. So somehow you have to land, and there's a lot of tricks to that. But to return something, that's even more difficult, because you have to send the fuel to get the thing back up into space, and then you have to have the fuel to get back to Earth. So this idea of returning a sample from Mars is going to be incredibly expensive. And
Yep. So we have a question from Jonathan. He says, was Mars seeded with water around the same time as Earth?
yeah, that's an interesting part of it, because we know in some ways more about early Mars than we know about early Earth. Because on Earth, there are no rocks older than about 3.8, 3.9 billion years ago. Earth formed 4.5 something billion years ago, and there are no rocks. We have rocks from Mars in our laboratories that are older than that. Those rocks came from Mars, not because we sampled them, but because there were impacts on Mars, which has a lower gravity than Earth, and the objects were thrown into orbit. Those objects came in meteors to Earth. So we have samples of Mars already, and some of them are older than any rock we have on Earth. We also, the surface of Mars, like this heavily cratered highland, these heavily cratered highlands average about 4 billion years old. In other words, this is a surface with the craters that are older than any rock we have on Earth. So we can find out from Mars things that were going on in the solar system that happened before we have evidence of them on Earth. So there's a way to think back and forth between Mars and Earth. So this data about water on early Mars, this is very important relative to how early water worked. Although we don't have rocks older than 3.9 billion years, we have minerals on Earth that formed that long ago. And there's a very resistant mineral called zircon. It's actually a gem. But zircon is very hard, has inclusions in it that can tell us that water was present And some of the zircons are as old as 4.4 billion. So we know Earth had a lot of water early in its history, like Mars. And all of this is going on now. Not a lot of it gets into the news. And even when it gets into the news, it is often not told in a complete context. It's sort of just gee whiz of stories. Yeah.
So can you talk about when the water was liquid on Mars?
Well, when the water was liquid, there are some that think there's little bits of water that can be liquid even today. This is controversial, but there are patterns that develop on some of the hill slopes of Mars that could be brines that are so lower the sort of melting point for ices so much that you actually get a little seep and flow. There's also, because we know there's a lot of ground ice, I showed, the radar images that show there's lots of ice. If you have any kind of hydrothermal activity where any kind of heat from interior Mars comes to the surface, you will melt that, and that water will flow. So the big outflow channels, the biggest flows, and many of the valley networks are more than 3 billion years old. But there were later episodes, not so spectacular, but for example, the alluvial fans, some of them on Mars are much younger than the time of the big outflow channels. So there are now a lot of work trying to work out this history. How did when was the water active? When was it more active? When was it less? The history of water is closely tied to the history of volcanism on Mars, because a lot of this water is associated with the internal heat that's being released by the planet. And there's also factors of heat that could be associated with radiatively active gases in the atmosphere. Mars's atmosphere is CO2, but there's evidence that at times in the past, the atmosphere was thicker and may have had methane, which is a much more effective greenhouse gas than water. All of this is part of a whole lot of people trying to figure out how early Mars was working.
What was the temperature? You're talking about water, we're talking about ice.
The surface temperatures of Mars are averaging over the whole surface below freezing at every latitude, except some equatorial parts of Mars go above freezing in part of the summer. So it's extremely cold. The other thing that makes it unlikely that water is going to be sitting around on the surface is the atmospheric pressure is so low that even if you had ice, it would be sublimating away. But you cover that with debris, or you put it in the subsurface, and you have ice. If you go deep enough in the subsurface, the temperatures are high enough, you have liquid water in the subsurface. Or near any volcanic area, you're going to have liquid water. So basically, Earth is at the ideal point average for its surface for water. And if you look at Earth from space, what do you see? You see the poles that are white, you see blue ocean, and you see clouds. You look at Mars from space and you see dust, and you see dark volcanic rocks, and you see dust-covered areas. Obviously, from space, the planet you look at that we call Earth, you would call that one Mars. You would call that one water. And the planet Mars would definitely land, and that Earth we often associate with the land. So the two planets got the wrong names because we only started looking at them from the ground up. If we were looking from space down, we would give them different names, but we didn't do that.
But you said the water flowed from south pole to the north pole.
But that was 3.5 billion years ago or more. That was under different conditions than operated today. And part of the problem is finding out how that worked, because the atmosphere from then is gone. So we've got to use other techniques to try to figure out what that atmosphere was like. One of the thoughts is that Mars had a denser atmosphere in its early history, and that it had these radiatively active gases like methane in the atmosphere. That's one idea, but it hasn't been definitely proven yet. Yes?
I have a question about the features that you showed where it seems like the flow came from underground.
Right.
Do you see anything that looks like that on Earth that would be helpful?
We see water bursting out of the ground when there are tectonic factors, basically Earth movements. This happens during earthquakes. You get water that squirts out of the ground. You can get water squirting out of the ground from hydrothermal activity. It's called geysers. And geysers operate with a plumbing system, and the energy that blasts it up is heat. You get water that flows up in glaciers where there's pressure that can drive the water up to higher levels. It's thought that with meteor impacts, you could mobilize ice from depth, from the heat of the impact, and force water out. But we don't have meteor impacts going on Earth the way they were going on Mars in the past. But where they have occurred, there's some evidence that there was these water kinds of activities. So the things on Earth that might do this are smaller in scale, but we've only been observing them on Earth in relatively recent time. To understand, we have to modify to the way Mars operates from the way Earth operates. And Mars has, although there's similarities, there's also big differences. The water coming up on Earth is resisted by gravity. Mars's gravity is much less than Earth's gravity. So it's easier to lift stuff on Mars than it is on Earth. There's a whole lot of factors that could come into play, and we don't understand exactly what they are because we can't see the underground on Mars. We hope to have ways to do that. One of them is radars. There are various abilities to penetrate Mars with radars. But there is evidence that there are big caverns on Mars because of the water that is disappearing into those big caverns. If they were filled with water and, let's say, heat was forcing that water to the surface, filled with ice, heat was melting it, forcing that water to the surface, that's another way to get that water to the surface. Lots of ideas, not a lot of ways to check those ideas. Okay.
Are there any other questions?
Nothing more.
Nothing more, okay. I want to thank you so much for coming to see me. Dr. Baker.
Yes.
And I've had prepared for having that chat.
Oh, no, it's okay. Yeah.
Thank you so much.
Yeah, well, thank you for the invitation.
All right, that wraps it up. Thank you all for joining.
Oh, cool.
Yeah.
I'll put it